Today we're going to start chapter number 10, and chapter number 10 talks about galaxies and the universe. The outline, the first part will discuss the nature of the Milky Way galaxy. The second, the family of galaxies, and then the third and final part will be about cosmology. So in the first part, we're going to look at the nature of the Milky Way. And as you can see here, that's basically an image of what we can see. Almost everything we see in the night sky belongs to the Milky Way from our point of view here. And of course, we see most of what we see, it's faint because it's very far away. And what you can see basically a band like this. And I think in a previous lecture, I told you that's what it looks like, a spilled milk or a way of milk, and that's why we call it the Milky Way galaxy, translated from Via Dilatata or something like that. Now, we are inside the Milky Way galaxy, so we do not have a view of it. We can construct a view of it. But if we look at our next neighbor, which is Andromeda, and that's how it basically looks like from outside, and that gives an idea of how we can basically look at our own Milky Way. Now, the first studies to basically map out what we see in our galaxy, it was attempted by William Herschel in 1785. And of course, he used optical observation. Remember in chapter number 5, we talked about electromagnetic waves that range from gamma rays, X-rays, ultraviolet, visible light, infrared, radio waves. Okay. For a very long time, humans were only able to use visible light. They did not basically consider the rest of the electromagnetic radiation. So that's why we say here it's basically based on optical observation. The closest to us, of course, our star is the sun. And he started trying to map out what he sees in the sky and trying to put a map of what they can basically see in the night sky with the telescope. It was at that time believed that our Milky Way resembled what we call the grindstone. A grindstone is something that usually used to grind grains, and where the sun is basically close to the center. That at that time, of course, the view now changed. Now, the structure of our Milky Way galaxy looks like a disc shape here, and we call this galactic plane. And galactic coming from galaxy. So that's basically the galactic plane for us. And this is where we have the galactic center, which is the center of our galaxy. The structure is hard to determine because we are inside. Distant measurements are difficult. We cannot do, we look at things that are far away and we get really accurate measurements. And our view toward the center is obscured by gas and dust. So there is something here. When we try to look at the center, we have lots amount of gas and dust that basically obscure our way of looking at the center of our own Milky Way galaxy. So what are the strategies that are used in exploring our Milky Way galaxy? The first one is select a bright object that you can see throughout the Milky Way and trace their directions and distances. The second, observe object at wavelengths other than visible light. So Herschel was only considering visible light, but now we can look at other electromagnetic radiation as well. And this basically to circumvent the problem of the optical obstruction that basically happens around the galactic center. And of course, again, we catalog their direction and distances. Then the third, it traced the orbital velocities of the objects in different directions relative to our position. So these are some strategies are used to map out our or to explore the structure of our Milky Way galaxy. Now, in the Milky Way galaxies, we have clusters of stars. And we have two types. We have what's known as the open cluster, and usually made of young stars of recently formed stars within the disk of the galaxy. And then we have something else that we call a globular clusters, and they're old. Okay. And they're usually centrally located or concentrated and in the halo around the galaxy. Okay. And we'll talk about the halo later on. So usually stars will cluster on with themselves. The globular clusters are basically made of old stars. That means, remember what I told you about I told you that the age of our universe is approximated to be 14 billion years. Okay. Now, these old stars are approximated here to be around 11 billion years. That means it's from the early formation of our universe. Now, when we look at the globular clusters, they're dense clusters, 50,000 to about 1 million stars. Okay. That's the cluster. Old, about 18 billion years, and they are lower main sequence stars. So the stars that we have there, if we look at the HR diagram, they will be lower main sequence stars. We have approximately around 200 globular clusters in our Milky Way. Now, when we try to look at the center of the Milky Way, we basically can look at these globular clusters, clouds, and that's what basically obstructing our view of the center or our galactic center. So maybe we have to look at other forms of electromagnetic radiation to circumvent the obstruction of optical observation. Now, this is basically the structure of our Milky Way galaxy. It's a spiral like this. The radius about 100,000 light years, but now it could be about 200,000 light years. It depends on from time to time, the estimates are varying. Now, when we look through the galaxy, this is basically face on, and that's basically the edge on. So you can see that the location of the sun is around here. That's our star. So we're actually in one of the arms of the galaxy, and that's what makes it very hard for us to map out our own galaxy. Now, at the center here, we have something that we call the nuclear bulge, which is basically, when you look at it face on, is this way. And we have something that we call a halo, and this halo basically around the galaxy, and this is what plays a role in extending the diameter of the Milky Way galaxy, or even increasing the number of stars that we have within our own Milky Way galaxy. So that's where the sun is. That's basically the disk face on, and this is basically edge on. And this is where we have the nuclear bulge. And this is what the halo is around and the globular clusters are basically located somewhere around the galactic center or around the nuclear pulse. That's another view here. You can basically look at the nucleus, and you can look at different spiral arms, and some of these spiral arms are basically given names, and these names are basically coming as a result of the constellation that basically exists there. Okay. And that's where the sun is located. That's the Orion, and I told you in a bonus where you have to look at Orion's around 10, 11 midnight, probably it will be exactly on top of your head. So that's a survey of our own Milky Way galaxy. Of course, what you see in here or what you see in here, it's not really a direct image. That's a constructed image based on energy that we collected from visible X-ray, gamma rays, radio waves, infrared, and all these type of energies. And then we conceptualize of how our Milky Way galaxy looks like. Now, what do we have there? Of course, we have stars, and we call that the stellar population. And we have two types. We have what we call population 1, and these are young stars, and they are metal rich, located in the spiral arms like our own, the sun. And then we have population 2, and population 2, basically the old stars, which is around 11 billion years old. And they have poor metal concentration, and they're located in the halo, the globular clusters, and the nuclear pulse. Now, sometimes people get confused. They should say, well, this should be population 1 because these are the early stars, and population 2, these are the stars that came later, but that's now what we convention that we use. So population 1 are basically the stars that come later, like our own, and population 1 are basically the old stars that range in about 11 billion years old. So you have here a table where it gives you population 1 and population 2. It gives you the metal concentration, the shape of the orbit, the average age in years. Okay, so you can look at this table here, and you can basically look at the differences between these two type of populations. Sometimes what we do to map out or to map out these arms or to look at the distribution, we look at something that we call OMB associations. And you know that spectral classification of stars. In the last chapter, I told you that O, boy, and F grade kills me. That means O is the hottest, and then the next hotter stars are B. So we look at these hot stars, okay, which will be brighter and hot in temperature. They're usually probably bluish in color as well. So we try to look at these to map out the arms of the galaxy, and we say that we try to look at distances to O and B association, determining, okay, or we can use something that we call Savai variables, type of stars that we talked about. We call these variable stars. And you try to use this as well to locate other stars, maybe closer to our sun or on different arms and so on. So what you see here, we see O and B association traced out for 3 spiral arms near the sun. Again, I have to remind you that we do this, or we draw this based on the different energies from different electromagnetic waves. So each one here is given a name, and the name basically has to do with the constellation that are located there. This is now here is a view of our own galaxy, or the Milky Way galaxy, if we only look at radio waves. Okay, not visibly, we look at the radio waves, and when we look, this is basically a wavelength of 21 centimeters. So you have a radio telescope that can basically operate at this wavelength, and you try to trace out the radio radiation, and again it gives you the disk shape of our own galaxy. Now the 21 radio observation, and when mean 21 centimeters, that means the wavelength is 21 centimeters. Well, this can gives us the distribution of a neutral hydrogen throughout the galaxy. And this is basically what you can see here. Distances to hydrogen clouds determined through radial velocity. That means we use the Doppler effect and we do this measurement, and that's of course we're going to give us the distribution of this neutral hydrogen in the spiral arms. Now, if you look here, that's basically the gamma rays, the energy that we can detect in the gamma rays. Here, the energy that we can detect in the X-rays. This one, of course, our visible light. And this one in the infrared. And this one is radio. So usually what we do is we combine all of these together to come with a conceptual image of what we think our galaxy looks like. And we talked about the use of different electromagnetic waves in astronomy. And I told you it's best if we go outside the atmosphere of the Earth, where we can basically get the gamma rays and the X-rays. Okay. For infrared, maybe it's also best if we get outside the atmosphere of the Earth. Radio and visible light can be done from here, but it's also better if we do it, let's say, from the Hubble telescope. And radio, again, we can do it from here. With this, basically, how we map out our own galaxy, and that's how we get to the structure that we have now. And that's a big change from the early Williams Herschel view, that basically the galaxy looks like a grindstone. But he started that, okay, and he wanted to basically get on how stars are distributed around the sun. This is basically a survey of our own Milky Way galaxy. Of course, we are not the only galaxy, as we discussed in chapter number 1. We said we live in a universe, and the universe is made of filaments. Okay, and these filaments are made of clusters or superclusters of galaxies, and of course the supercluster is made of cluster of galaxies, and we live in something that we call the local group, and it's about 21 galaxies. One of them is the Milky Way. So we have lots of galaxies in the universe. And how do we basically look at these galaxies? Okay. So usually these galaxies are star systems like our Milky Way. That means these galaxies are made of stars. They contain stars. They contain few thousand to tens of millions of stars, or 100 millions of billions of stars. In terms of shape and sizes, they vary in shape and sizes. Now, when we look at the sky, we can see stars at night, but we can see lots of emptiness there. It's an empty, it looks like there is nothing there. But if you basically do what we call a deep field, you take an area which looks like empty in the sky, but you take a large, big exposure time. And this is done by the Hubble telescope. And we talked about the Hubble telescope, and we said the Hubble telescope basically is orbiting the Earth. So it's not obstructed by the atmosphere of the Earth. And what you see here, it's a 10-day exposure of what seems an empty field in the sky. And you can basically see all this huge number of galaxy in this area that it seems to be empty. But of course, you have to wait for a long time. And that's when we talked about light gathering power. Okay. So this region, which basically seems to be empty, it contains nothing. But if we take a long exposure time and enhance the images, we actually can see galaxies. And these galaxies, of course, they have either what we call spirals or ellipticals, okay, or something that we call irregular. And these irregular galaxies, they come from the merger or the collision between galaxies. So in the classification of how we classify galaxies, we can look at them as either ellipticals or spiral. And you know, when we talked in chapter number 6, when we talked about ellipse and we talked about circles in 3 dimensions, of course, you can talk about ellipsoid and you can talk about sphere. So now, when we, in chapter number 6, we said the elliptical shape is basically when you take a circle and you deform it. So the same idea here, if you take a sphere and you stretch it a little bit, it will become what? It will become elliptical, and that's why we call them ellipticals. So E0 and E here stand for elliptical. E0 means it's a spherical in shape. And it could go all the way to E7. And E7, it will be basically something elongated where it gives you the shape of elliptical. So you go from the spherical, which is E0, all the way to E7, which we call highly elliptical galaxy. So what you see here, that's an E1, and that's basically an E6. You can see the difference now. It's really elongated, and it gives you the shape of the elliptical. Spirals, which is like our own, it's basically, you can see a disk-like with a large nucleus around it, and then it has arms. In this case here, the arms are very tight or very close to the bulge, and that's what we call SA. And in the case of SS, okay, you have a smaller nucleus and loosely wound arms around, like our own here. So that's basically the spirals. Some of them are, the arms are very close, some are tightly wound around the nucleus, and in our case here, it will be far away from the nucleus. So spirals are rich in gas and dust. Ellipticals are almost devoid of gas and dust. That's one difference between both of them. And galaxy with a disk and a pulse but no dust are termed as S0. We have another type, which we can basically say it is bar spiral, which basically it has what it looks like a bar in the middle, and then you have 2 arms spiraling around this. And in the sequence, we can basically use a spiral. B here stands for bar, so we say SBA all the way to SBC, like what we did in the previous slide here where we said SA and SB and SC. That means the different types. Now we put a symbol B in the middle between the S and the A, and to indicate that it is a bar spiral analogous to regular spirals. And then we have what we call the irregular galaxies, and these basically come as a result of collision between galaxies or mergers, when two galaxies merge together. Okay, and it's always a region where you have very active star formation, because you'll have lots of gas and dust and so on. For example, we have here the Cocoon Galaxy, the Large Magellanic Cloud. Usually, sometimes in astronomy, they have names because you have large numbers of galaxies, so they give galaxies. And some of them are small, where we call them dwarf galaxies. And they actually become a satellite of larger galaxies. Everything in our universe is moving. Nothing is stationary, okay? So it's, remember when we talked about binary stars and we talked about Sirius A and B, and we said Sirius B is a white dwarf that orbits around star Sirius A. Here it's the same thing. These white dwarfs, they might themselves like a satellite, like a moon, where we have the moon around the Earth. They will be basically orbiting larger galaxies. So there is what we call Hubble fork diagram. He came up with a diagram to basically show this family of galaxies. So we start from the ellipticals, and this is the E0, which looks like spherical. And then you go all the way to get to what? To get to E7, which is highly elliptical. Then you come to the spirals, and that's what we call S0 here. And these will go into two types. We go into the spiral shapes like this, which is SA, SB, and SC, or we go into the bar, which like a bar, spiral and two arms at the end. And then we have here, which is not basically in this fork here, but we put it there, and this is what we call the irregular. And this could be any two types that collided or merging with each other and so on, so they don't have a regular shape. And this is known as the Hubble fork diagram. Hubble was basically the scientist who discovered that galaxies are receding or moving away from each other. So Hubble start basically looking at distance galaxies and how they are moving away from our Milky Way. And he measured the recession velocity, which is called VR. That means how far they're receding from our own Milky Way. And he started basically measuring their radial velocity, or the recession velocity, and their distances. So we measure the distances in something that we call here mega per sec. Just to give you an idea, a parsec is a very large distance. 1 parsec is equal to 3.26 light years. So we're talking about huge distances here. Now, when we say kilo per sec, that means 1,000. When we say mega, we're talking about million. And when we take about giga, you're talking about a billion. So here we're measuring distances in mega per sec. And you know that the parsec is about 3.26 light years. So we're talking about huge distances. And he came up with a relation that this VR basically equals to H naught multiplied by D, where VR is the recession velocity, and D here is the distance, and that's what we call the Hubble constant. And the Hubble constant here is about 70 kilometer per second per mega per second. And the reason here, we're looking at the velocity measured in kilometers per second. And here we're looking at the distance, which measured in mega per second. So the H here will come from the slope here. And this relation here, the H will be the slope, and the slope basically will have the rise over the run, and of course the units of the rise are kilometer per second, and the units of the distance in mega per second. And from this later, I show you that we can measure basically the time or the age of the universe later on. That's how we obtain the age. But that's how Hubble was basically measuring how the stars, how the galaxies are receding away, and at what rate, and their distance, and so on. And he came with this. Of course, the measurement of the VR is coming from the Doppler effect. And we talked about this from the Doppler effect later, that remember when you look at something receding, it had a shift and so on, and we were able to decide on the radial velocity. And of course, from this, we can also find out the distance. And that's what made Hubble or Edwin Hubble successful in measuring these. And later on, when the telescope was launched in 1990, it was named after Hubble, or called the Hubble telescope, in honoring his discoveries. So on a large extragalactic distance scale, you can basically see many galaxies, okay, typically millions or billions of parsec from our own galaxy. That means a huge distance from here. I told you 1 parsec is 3.26 light years. Typically, the units that we use, mega parsec, that means 1 million. You know, mega is 10 to the 6, or giga, which is about 1 billion parsec. And distances of mega or giga, that means the light we see left these galaxies millions or billions of years ago. So when we take this deep field view and the long exposure, actually we are not seeing them right now. Like when I told you about the stars, we're basically seeing them because we have to wait for that light that comes from there. So we're actually seeing this in terms of millions or billion of years away ago, and that's why later I'll show you that we can get basically at the age of our universe. So we are basically looking back in time, in the past, to see what was our early universe looked like. That's basically the galaxies now. So we don't have only, we live in a galaxy, but it's not the only galaxy. The universe is made of galaxies, and these galaxies are moving and they're receding away from us. And we can basically try to use the Doppler effect to measure at the rate, at how much rate they are receding away. We can basically look at their distances, and we can get a relation between this receding velocity and distances, and you can see in this graph here. And it gives us an idea to look at different shapes of galaxies and their families. They basically range from ellipticals to spirals and to the irregulars. And I showed you the fork done by Hubble to give you the family of galaxies. In the third part here, we're going to concentrate on cosmology. Okay? And we can look at the Hubble or distance stars that are basically receding away from us, and this is what known as Hubble law, and you can look at how they are basically receding at us. Now you can see here different names: Virgo, Ursa Majoris, and these are the names of constellation, and that's where you can basically locate these galaxies, and it gives you here the speed at which they are receding. The speeds are very high. We're talking here 1,200 kilometers per second, and of course you're going to apply their distance and their speed. And in the y-axis you have VR, and the x-axis you have the distance in mega per sec. So the view now, how are these galaxies basically are receding away from each other, which gives an idea that something is expanding. Okay. So we say that the space is expanding and carrying the galaxies along. That doesn't mean the galaxies are expanding. Okay, they are moving. Okay, through space, and the space basically is carrying them away, and that's why they are receding from one another. So the common view now that the galaxies themselves, they are not expanding, but what's expanding is a space. So you can look at the image that we have here, and then you have after some time, it's basically they have drifted away from each other, and because the space is basically is expanding. So that's one way when you look at a point in space, and then it starts moving away, it's expanding. So that's how space has taken these points away from here. There is an analogy, and the analogy is called the raisin bread. So you take and you want to bake a loaf of bread, and you put raisins in it. And once you start baking, it will basically expand. And as it expands, basically, it will these points will go further away from each other. So the raisins here themselves, they did not expand, but what expanded is the bread, and it carried out the raisins with it, and that's basically what we conclude about our own galaxies. They're basically the space is expanding and it's carrying them away. Many times people try to use an analogy of taking a balloon and you put a little bit of air and you put 2 dots or 3 dots or whatever on the balloon, and then you blow more air, the balloon becomes bigger, and these points will basically become further away from each other. They tell you that as the space is expanding, these basically are moving away from each other. Okay, as you can see here, that doesn't mean we are at the center of the universe. When we see these things are receding away, you can basically think of that what I told you here, like the raisins, they're moving away, but that doesn't mean this raisin is the center. The same way at the balloon, you are moving as they are moving, but that doesn't mean you are we are at the center of the universe. And maybe if someone doing the same observation somewhere in a different galaxy, they will actually get the same way. They will see us as moving as well, and everything is receding away from them, but that doesn't mean they are the center. So you know that when we discussed this earlier, we told you that in order civilization, they thought maybe we live in a geocentric universe, and geo means Earth. That means the center of the universe is the Earth. And the view was changed to heliocentric universe. That means the sun is the center, but that only can explain why the planets are basically orbiting the sun. Now we know that the sun is one from 200 to 400 billions in our own Milky Way galaxies, and we have billions and billions of galaxies in our own universe. So we don't really know where the center is of the universe. So now, when it comes to deciding on the age of the universe, remember what I told you. We look back in time. We try to basically look back in time. Okay, what happened? And if I take you back here, and this analogy here, when you can see this image, you can also go back and you can basically take it back, take it back, take it back. You may go basically to a small point. Okay. And everything originated from that point. So sometimes people are trying to measure the age of our universe, and you're all familiar that basically when you try to calculate velocity should equal to distance divided by time. So if you want to get time, it will be basically going to be distance divided by v. And that's what we have here. We basically have here time is going to equal to distance divided by velocity. And if you recall what we had previously, we said that VR equal to h naught multiplied by d. And this is what I wanted to get. So my velocity here, from this one here, if I look at what I have here, my velocity here, d over t, which equal to d over v, it will give me 1 over h. Because if you want to divide d, or you want to divide d by v, you will basically going to get 1 over h. And from basically deciding on the h constant, and that, remember earlier I told you it's about 70, that roughly gives you about 14 billion years. And that's how we get at the age of our universe. Now it's approximated about 13.8 billion years. And this is how we, because from this expansion and so on, and from this constant, we can basically get at the age of our universe. Of course, you may actually look at current research that people are doing, and they're trying to go, yes, if we go back to a very small point, which is infinitesimally small point, and we had nothing but energy, and then after that explosion, matter start forming, and you get to the elementary particles, and then you get to hydrogen. Now there is still debate. What we see here is actually it goes to matter. We cannot go back to that point. So there is lots of interest now to know exactly what happened in this early part of the universe. Okay. So the most distant galaxies to us, they may actually form about 1 billion years after the Big Bang. So that's what we see. We look at this galaxy, but it's basically 1 billion years after the Big Bang. What happens if we want to get earlier and earlier and earlier and go on? Okay. And that's now a big area in research where they're trying to see what happens between the initial and the formation of elementary particles. So if we try to look back toward the early universe, that means looking at things in the past, okay, the more distant objects that are far away from here. They happened basically when the universe was forming. So when we look back, we can basically look at, for example, if we're looking this from the Milky Way, we can basically look into what happened in the past in terms of what we call back radiation and so on. And we can, if we go back in distance, we can basically measure time, and we get to the age of our universe. R. Wilson and A. Pentas, they measured radio waves using a detector that they borrowed from a company. And they were basically measuring something that we call back ground or cosmic microwave background, and they give a temperature of about 2.7 Kelvin. At the time when they basically were first observing this, they thought this is something that noise or something like this, and then they became convinced that, or physicists basically stopped making calculation and so on, and they basically said this is actually coming from what we call cosmic microwave background, and that's coming after the Big Bang. And they measure this radiation, and this has the temperature. This is now the COBE satellite map the structure of the cosmic background radiation to get basically at one of these things that basically give us an idea that the universe started from a Big Bang. So we can get at the age of our universe from the rate at which the galaxies are receding. But there is something else when we try to look at the effects of gravity in our universe. Now, you're all familiar with, you heard about Newton. The story goes that an apple falls down, and we call that free fall. And he said basically it has to do with the gravity, because the Earth attracted the apple, and he said when two masses basically attract each other, and he discovered some gravitational law, and he explained why the planets are orbiting the sun, but the planets are basically far away from the sun, and it looks like this attraction happens at a instant, but it happens at large distances and so on. Einstein basically has a different view. He said, well, gravity comes as a result of bending space. If you take a sheet of anything like cloth or anything and you put a mass, the mass will basically make a dent in it. It will curve it. So the view there from Einstein was basically the curved space basically is the result of what it looks like to us. It is gravity. So mass is important there. Mass is basically creating this. So when we make observation and we look at the visible mass that we can see, and we try to predict what will happen with it with our observation, we always, or scientists conclude that actually there is some mass missing. These affects, we should have more mass there. And when they looked at, for example, some of the clusters, they said this clusters, they should contain 10 times as much mass as is directly visible. What we see is about 1/10 of that. We don't see the total mass. This is some clusters. Okay. So if we combine all the visible mass, which gives us matter, what we call matter, okay, emitting all kind in the universe, it will add up less to what we call a critical density. Things that would basically make sense if we want to include in the masses. So for example, you look at the sun here, and that's what's measured. The sun basically, it's rotating around itself, and it's also moving in our own galaxy. So that's basically the effect that we see on the sun. In this case, we look at the rotational speed, how the sun is rotating. We look at the distance from the galactic center, okay, and we try to look at the effect of this mass. This is what is measured, but if we want to calculate that, we should basically have something like this. That's we call Keplerian motion, according to Kepler's law. Remember when we talked about Kepler's law in chapter number 4. Now, this is basically, when we look here, that's if we just look at our own observed mass. That's how it should happen. But it basically behaves in this way. That means we have extra mass that we don't see. And that basically came in the conclusion that what we don't see in terms of mass, we call that dark matter. So now it is approximated that our universe, it's made of about 4% visible matter. That's what we see. We only see 4%. And 26% is dark matter. And 70% is dark energy. So actually, what we are seeing, we're only seeing about 4% of all the energy and the mass of our universe. 96% of our universe, it's still mysterious and it's not unknown yet. And people are trying to basically try to understand this dark matter and dark energy. So the idea here is we're trying to give you a flavor of what our own galaxy is, what are the other galaxies are, how we can measure the age of the universe from Hubble's constant, and the dark matter and dark energy that we basically, it's a big and hot topic these days. Any question on this? Any questions? Any questions? No questions? Okay, good.